This is our second example in section 3.4. We're looking at projectile motion here, so it's another object in motion. We're told here that a small rocket is launched straight upwards, and its position in meters above the ground is given by the function s of t equals negative 4.9 t squared plus 106 t plus 300. Okay, so we're launching this rocket straight up. I'm picturing, I don't know if you guys had these back in the day, but like a stomp rocket or a bottle rocket type of thing, where it's made out of a little canister or soda bottle or something, and you either pump it full of air or stomp on it, and it launches it straight up, and then it comes straight back down. They're pretty little rockets, like kid stuff. All right. So this might be a different situation than that. I think this particular function, it's actually moving a lot faster than those would have been. But yeah, that's just what I'm picturing. So we would like to find the velocity of this rocket at a particular point in time, at an instant in time. So we want instantaneous velocity. So that's going to be our function v of t, which is the derivative of position, s prime of t. And so we would use our power rule on this polynomial right here. You'd have negative 4.9 times 2t, okay, which I'll do that multiplication there. That would be negative 9.8 t to the first power. And then the derivative of 106t is just going to be 106 times 1, all right? And the derivative of 300, being a constant, is just 0. So that is our velocity function for this rocket at any point in time. So to find the velocity at the point in time 3 seconds into the run here, we're going to plug in t equals 3. So s prime of 3 here would be negative 9.8 times 3 plus 106. All right. And when we crunch those numbers, that would turn out to be 76.6. And our units here, what are our units? Check what your units for each thing are. We have position in meters and we have time in seconds. So position changing over time would be meters over seconds. And so that's our unit for velocity. So 76.6 meters per second. All right. And the positive nature of that indicates that this rocket is traveling currently in whatever we've decided the positive direction is, which is usually up. Okay. Now in part B, we want to find the acceleration and the jerk of this rocket, time t equals 6 seconds. Let's start by finding our acceleration function, because acceleration is the next derivative. Okay, it would be the derivative of velocity, v prime of t, or you could think of this as the second derivative of position, same thing. And so when we do that, we'll be taking the derivative of this function right here. And that first term, derivative of negative 9.8t, is just going to be negative 9.8 times 1, but that would be negative 9.8. And the derivative of 106 is 0, so that doesn't have an impact here. So we end up just getting a constant acceleration. Our units on this are meters per second squared. Okay. And let's note this is a constant acceleration. And notice that this is negative, which indicates that that acceleration is pointing in the negative direction. So if we just decided that upward was positive in looking at our velocity, then acceleration would be acting this way in the negative direction, causing that rocket to be slowed down if it's traveling this way, or the rocket would be speeding up if it's traveling downwards, like at the end of its flight. So that acceleration there, that constant acceleration, is actually due to gravity. So that's why it's pulling back downward. All right, it's pulling back down towards the surface of the Earth. Okay, and that negative 9.8 or 9.8 meters per second squared, that is a constant that we looked at earlier on here. Yeah, there it is. Acceleration due to Earth's gravity. There's our 9.8 meters per second squared. And so that's exactly what we're seeing in this rocket problem. Okay, so that hopefully makes some sense. All right, and then that's our acceleration, that's due to gravity. Let's find our jerk. Oops, I guess it does say one more thing before we get to jerk. It does say time t equals 6 seconds. We didn't even plug in t equals 6 here because it was a constant acceleration. So I really should have done that here. Acceleration at 6 seconds is negative 9.8 meters per second squared. Okay. It's still a constant acceleration. There isn't any outside forces causing this rocket to accelerate, like a booster pack or anything like that. But yeah, there's our acceleration. Now let's look at our jerk. Okay. So jerk, remember, is the next derivative. It's the third derivative of position. Or we would be taking the derivative of acceleration, a prime of t, or s triple prime of t. And so to take the derivative of this constant function is just going to give us a 0. Okay. And again, we've ended up with a constant function there. So even when we plug in time t equals 6 seconds, all right, that's going to be 0. And the units on this, remember that it is changing acceleration over time. So meters per second squared per second. That would be meters per second cubed for those units. Okay. And the fact that this is 0 jerk, there is no jerk, all right, that's because there is no change in acceleration. It's just gravity acting on this rocket in a constant acceleration form there. So, oops, no change in acceleration. There we go. All right, so no change in acceleration either in the magnitude or direction of that acceleration. It's always 9.8 meters per second squared, and it's always pointing in the same direction, downward, negative, toward the Earth. So there's our rocket problem.